electronicity all kind of centers around atomic radii trend. If you can explain atomic radii, you'll be fine for all the other trends. The only thing that you'll have to do is tie in your justification at the end with, because of these things, therefore, ionization energy is this, or ionic radii is this, or electronegativity. So we're going to do atomic radii, ionic radii, ionization energies, electronegativity. Electron affinity also applies to this, and I'll get to it later. Electronegativity is between two different between two different atoms in a bond, whereas electron affinity is for an atom with an electron nearby. So it's either bonded or not bonded, trying to get electrons. So same thing applies for all of them. All right, atomic radii, the general trend runs, and I don't like the way this slide looks. Sorry. Atomic radii, I'm doing the wrong trend, goes down here. So who's the biggest? Francium, right? So take your periodic table out so that as you're looking at this, you can kind of work through it. So francium has the largest atomic radii, and we're going to discuss all the reasons why. So just looking at this and looking at your periodic table, and then you'll look at the next few slides, it'll justify it for you. Going down a group, why is francium the largest? Yep. You're adding energy levels. It's like literally climbing up a ladder. As you go up the group, or down the group, you're climbing away from the nucleus. So if this is my nucleus here, and I add energy level 1, 2, 3, and so forth, I'm getting further and further away. So the further away you are from the nucleus, the bigger your atom is. That's a really simple one. All right, going from left to right across the periodic table. Yep.
Further left, the effective nuclear charge is lower, which means they're farther out.
Because what can't hold on to it as well?
Nucleus.
Yeah, so effective nuclear charge. And now we're talking Coulomb's law. So according to Coulomb's law, the less charge there is, the least, or the weaker the force of attraction there will be from the nucleus to the outer shell. So take sodium, for example. We have sodium with 11 protons, and then we have neon having, I'm sorry, in the wrong group, argon with 18. Wrong period. 18 protons. So I'm not talking about the fact that there's 18 electrons and 11 electrons. I'm talking about that they're both holding on to the third energy level. So here's 3, 3. So because you can see that this one clearly has more effective nuclear charge, more charge there, this has a greater force of attraction. So it's like me on a tug of war, pulling the nucleus, holding on to that outer shell way tighter than the 11 protons can pull on it. So because this has greater effective nuclear charge, and according to Coulomb's law, a stronger force of attraction, it can hold its outermost energy level tighter than this one, which has fewer protons and a weaker force of attraction, and so therefore it's larger. On the exam, what will be hard for you to do is understand how to justify. When you get a question that says justify, you have to talk about both of them. So if I say, which of the following has the greatest atomic radii, sodium or argon? You can't just say sodium because it has fewer protons and has a weaker force of attraction, therefore its hold isn't as great and it has a larger radii. You'll get half the points because what didn't you do? You didn't talk about argon. So whenever you're justifying and comparing and contrasting, you must discuss both. Does everybody get that? Why don't you write that somewhere so that you remember tomorrow you have to explain both. All right, so if you look at the next slide, this is just what I said verbally to you. It says going down a group from top to bottom, new shells are added. The principal quantum number increases. Principal quantum number is that n equals number. So n equals 1, 2, 3, and so forth. So you get larger orbitals. How come the orbitals themselves get larger? Huh? Yeah, there's more electrons, but what about that shell is getting bigger itself? What are you adding to it? Each shell gets more subshells. So like the energy level 2 has 2s, 2p. Now I've added 3, which can have 3s, 3p, 3d. So the more subshells you're adding, the greater that radii is getting also. Valence electrons have more energy, are less stable, and are further from the nucleus. The outer electrons experience a greater shielding effect and decrease effective nuclear charge. So they're getting shielded by energy level 1 and 2. If I'm in 3, I'm shielded by 1 and 2. But within 3, I'm also shielded by my own orbitals. So D is shielded by P and S. P is shielded by S. We talked about that last week. Remember that? So within an orbital, you experience that shielding too. And then according to Coulomb's law, the force of attraction decreases as the distance between the electrons and the protons increase. So we're talking about charge also, effective nuclear charge, but that's for the period trend. So for the distance trend here, that would be going down a group. So you could still add in, according to Coulomb's law, as distance increases, force of attraction weakens. And then the next slide is discussing going from left to right. So again, Coulomb's law, effective nuclear charge, protons are added, and all that is written there for you. You also get that shielding effect for valence electrons in the same shell, same thing we just talked about. And so just make sure you incorporate the Coulomb's law, effective nuclear charge, and then force of attraction. Those would be your 3 main words that you want to kind of add into your explanation when you're defining and justifying. Questions? So if you understand the atomic radii trend, everything else comes easily. So let's see if that happens for you. Ion formation. Anytime that you're making an ion, you are either gaining electrons or losing electrons, right? So if I gain electrons, I become what? What's that ion called? An anion. If I lose electrons, I become what? A cation, right? So this is metals losing electrons to form cations, and this is just the general way we write them. And then this is nonmetals gaining electrons to form anions, and then again, that's how we write them. You know that, right? So you saw that in your homework. I think in one of the lectures we just used A for atom, but you can do it for any individual element. All right, so we're going to talk about what happens when you gain and lose electrons. You know this, metals, nonmetals. I give you one, you can figure out if it's gaining or losing. Nonmetals are always going to gain electrons. Why are they gaining electrons? They want to fill up their valence shell, right? They want to get to 8 octets. Or noble gas configurations. Who does not want 8? Which element does not want 8 electrons? Hydrogen, because hydrogen wants to become who? Helium, which only has 2. All right, this is a new vocab word for you, isoelectronic. Isoelectronic just means that they have the same electron configuration. So if something is isoelectronic with something else, it ends up with the same electron configuration. Like sodium cation is isoelectronic with neon because they will end up with the same electron configuration. So they have the same configurations but different radii, and then we'll talk about that. So argon has this configuration, but when chlorine gains 1 electron, it still has the same configuration. However, these two will have different sizes. This is also isoelectronic, right? Isoelectronic, but all of these radii will be different. As the ratio of protons to electrons increases, the forces of attraction of those electrons increase. So you can compare all of these to determine which one, and you can rank them in order of which one has the largest atomic ionic radii down to the one that has the smallest ionic radii. So let's look at the reasons why. All right, cations are smaller than their neutral atoms. So this is true because what happens when you became a cation? You lost or gained? You lose electrons. And electrons are that tug-of-war system. So if we're equal on both sides, so a neutral atom is equal on both sides, if I get rid of electrons, now me, the nucleus, can pull on you guys tighter. So what happens to my radii? Smaller, because I'm pulling it in. So my force of attraction is greater there. So as you lose successive electrons, that radii gets smaller and smaller and smaller. So the easiest way to do this is to just write out your number of protons with electrons and compare them if you're comparing 2 different ions. So this is potassium. Look at your periodic table where potassium is. It's in N equals 4. Once it loses its electron, what happens to it? Not just smaller because of proton-electron decrease their ratio, but it goes into the N equals 3. So once you lose a shell and that becomes N equals 3, that's like a whole nother huge reason why the ionic radii would decrease, right? The fact that I just discussed tug of war is true, but if you lose a shell, then it's that much smaller, like much, much smaller. Same thing here with strontium. Strontium is in period 5, but it's also in group 2. How many electrons does it need to lose to become a noble gas? 2. Once it loses its 2, it loses that shell. So it'll become much smaller. Okay. Anions are larger than neutral atoms. So what happens when you become an anion? Gaining or losing? Gaining. So now that tug-of-war system is happening, and I'm the nucleus, the protons, but you guys are adding on electrons. And so you now are pulling on me, and I'm getting stretched further out to you. So now my radii, my ionic radii, is going to get larger. You're not going to gain any levels at this point because you're just getting to the noble gas configuration, which is in the same period that you're already in. So you're never going to go another shell up, but you'll just get larger because the electrons are pulling on you. So here's the general trend written out for you. Going down a group from top to bottom, new shells are added, the principal quantum number increases with larger orbitals. Valence electrons have more energy, are less stable, and are further from the nucleus. The outer electrons experience a greater shielding effect and decreased effective nuclear charge. And then according to Coulomb's law, the force of attraction decreases as the distance between electrons and protons increases. So we're same stuff as atomic radii, but now it's just talking about ionic radii. And then the same thing for cations. The radii of cations decrease as the number of electrons remains the same. That's wrong. Fix that. Do you see that? What should it say? As the number of protons remains the same and electrons are added, are removed. Which one are we on? Cations? Yeah, that should say, right, the number of electrons are being removed and protons are the same. These are cations. This slide has an incorrect statement on it. So cations are when electrons are being removed and the protons remain the same. And then again, ionic radius of anions. This should be correct. Go ahead and read that. All right, any questions on that? Yep.
Like, what does it mean when it says that it continues to decrease? Like, if it increases, how does it decrease again?
Where do you see that statement?
The radii then continues to decrease.
Oh, okay. So when you first encounter the first anion, the radius increases dramatically. The radii then continue to decrease. Oh, this is going across the period. That's what it means, like continuing across the period. That's what it's saying. So now when we look at our general trend for ionic radii, our trend goes like this. So these are your metals. These are the largest. But then we also know that our nonmetals are going to be large also going in this way. So this is for your nonmetals, and these are for your metals. They have two different, obviously, functions how it's happening. But your largest anions are going to be moving to the left also. All right, let's take a moment. I don't think I've done this before, but let's go back to this slide and let's rank these just to see that you understand their trend. So sulfur, S-2, then chlorine, Cl-, argon, potassium+, and Ca+2 calcium. So easiest way to do this, instead of analyzing trends, is just say to yourself, this is 18 protons, because I'm looking at the periodic table. Chlorine has 17 protons. Sulfur has 16 protons. Calcium has 20 protons. And then potassium has 19 protons. How many electrons do they all have? 18, because they're all isoelectronic. Now, if you didn't have the electron configuration, you would tell yourself, well, this had 20 protons and 20 electrons, but it's 2+, which means it lost 2, so therefore it only has 18. So these all have 18 electrons. This is super easy to see once it's written out, isn't it?
Yes.
So who has the greatest hold?
So all the least amount of protons. No.
I should start with the largest, because I said go from the largest to the smallest. So largest would mean weakest hold, right? If it has the weakest hold, then it can't hold them tightly, so it would have to be, which one?
Which one are we
Yeah. We're going from largest to smallest. Largest has the weakest hold.
doing? Sulfur.
Yep. So do you see how that works? 16 protons holding on to 18 electrons. Then 17, 18, 18. Strongest hold here, which means it makes it tighter. Good? All right, so now I think you understand the trends. All right, moving on. So definitely you will need to do this on your exam. You will definitely have to pick and choose who's biggest, who's smallest, and then it will say justify. You cannot just show me protons and electrons like I just did. You can use that as part of your explanation, but you must include Coulomb's law, effective nuclear charge, and force of attraction, and distance. All right, first ionization energy. This is the energy that is required to remove an electron from the least tightly held electron from an atom or ion in the gas phase. So you must discuss in your definitions or in your explanations that ionization energy is the removal, the energy required to remove an electron. So whichever one requires the most energy to remove an electron is the highest ionization energy. Energy must always be added to remove an electron. Therefore, the values are what? Positive or negative? We talked about this before. Added energy. Positive, because released energy is negative. If you don't remember that, write it down again. So that means that these are all endothermic processes. I have to supply energy to remove an electron. If I release energy, it's negative. So here's our general trend. Ionization energy, the strongest ionization energy is in the top right. So now you can relate this to atomic radii. Why would it be hardest to remove an electron in the top right? It's not more protons. Like helium only has 2 protons. Yeah.
It's got a strong hold because that's the
Smallest radii. So the smallest radii has the strongest hold, the greatest force of attraction to its electrons in that n=1 shell. Therefore, it is requiring the most energy to remove that electron because it has the greatest force of attraction. So force of attraction, the strongest force of attraction will have the highest ionization energy, which means the smallest atomic radii will have the greatest ionization energy. So again, our same exact explanation for atomic radii is going to be used here, except it's just going to be a final statement that it requires more energy or less energy because of its size. So here's the slide that we saw last week too about ionization energies. Moving across the periodic table from left to right, ionization energy is increasing within each period because our effective nuclear charge is increasing, the number of protons. So as charge increases according to Coulomb's law, force of attraction increases, therefore it requires more energy for an electron to be removed as you move from left to right. Make sense? So we see these trends increasing as we go, and then Nelson, you mentioned it last week, and I talked about it a little bit. Why do you see that little dip there? So we jump from beryllium to boron, and we see we're at lithium going to beryllium, and then we do a quick jump like that. So this is boron, and this is beryllium. Why does the energy decrease for just a moment? Talk to your group. Why does energy decrease when we get there. Emily, do you know? Did you talk to your group? Nelson, do you know? You guys didn't talk about it. Talk to each other. OJ, you get it? No. Grace?
Yeah,
Shielding. If it weren't, right, if there weren't sublevels, if we still had the Bohr model, we would just see a continuous trend because all electrons are created equal in the Bohr model, right? But our electrons are not created equal when we have orbitals and sublevels because the p sublevel in that second energy level for this, is being shielded, p is being shielded by s. So for a moment we see that has decreased ionization energy because it's not that hard to remove that p1 compared to that 2s. Full orbitals are harder to remove electrons than their very next one. You'll always see that little dip right there when you get to the next orbital because of shielding. So this p orbital is shielded now by s, so it doesn't feel as strong as a force of attraction as the full s orbital did. Understand that? Okay. So we see a slight dip there. And there's some other, oddities there, but that's the general reason. All right, so here's a lot of words. First, ionization energy generally increases as atomic radii decrease. According to Coulomb's law, the force of attraction decreases as the distance between electrons and protons increases. And here's some exceptions. It requires more energy to pull an electron from a full d subshell than it does to pull the only electron in a p subshell when in the same period. It requires more energy to pull an electron from a full s subshell than it does to pull the only electron in a p subshell. This is this example right now. Beryllium versus boron. I just explained that. So a full s subshell is your beryllium. Your partially full was your boron. And that's because of shielding. Same thing that happens with the d to the p's. As you go to the D, you have a full one, you go to the P, you end up with a slight dip. That single electron is easier to remove as it is the only electron in the higher energy subshell and it is being shielded by the electrons in the lower energy level subshells. So we have S, we have P, and then we have D. So as you're adding, this is full, I have 2 electrons, and then I get 1 here. This is being shielded now by this. But then as I continue to add within this level, 6 of them, then you'll see the same ionization energy trends that you would expect, that it's increasing. Yes?
So is that only for one electron? Like if there was 2, would it still?
No, you'll just see like on the last slide here, you'll see it just follows that trend now. Like it was dipped slightly, yeah. It dipped slightly, but then it continues to follow the trend.
So it only works for that when there's 1 electron in the sublevel?
I mean, that whole sublevel is being shielded even with 6 electrons in it. It's just that your ionization energy is increasing because the atomic radii is decreasing. So energy increases as radii decreases. So as you add more protons, your radii is decreasing anyway. But the whole energy level still is shielded, but you only see it at that moment because the radii isn't quite as small and you got shielding going on at the same time, so you see a little bit of a dip. All right, the second ionization energy. What is second ionization energy? Energy required to remove the second electron. Successive electrons, which means I've already removed 1, now I'm trying to remove the second one. So the second ionization energy for an atom is always greater than the first because now it's just harder to remove it, right? There's the same number of protons, but now holding on to less electrons. So it's me versus you guys in tug of war, and then we just got rid of Argo, and now I can pull you tighter, right? And then as I get rid of the next electron, I just got rid of OJ, now I can pull you guys even tighter. So as that radii begins to decrease, decrease even more, ionization energy increases with each successive electron. So that's what this is saying. Every element has one extremely large increase in ionization energy. And when does that happen? Nelson?
After it reaches noble gas.
When you lose your energy level and you jump to the noble gas configuration of the one prior to you. Because what happened then? You lost an energy level, which means that you've gotten that much smaller. You just shrunk tremendously. So you'll see a huge increase in ionization energy because now your radii is that much smaller. So it says this occurs when the electron configuration drops the principal quantum number, which means energy level, which causes the radius to shrink much more than the other ionizations. So you will get questions that will give you atoms, and they will ask you what is the common charge for this. And it might not just say, like, what's the common charge of calcium, because we know that's +2. It'll make up a pretend one. What's the common charge of atom X? And then it'll give you a table of first, second, third, fourth ionization energies, and you have to examine the energies to see where that big dip is, or where the big jump is. Maybe it was like 400, 1400, and then 7,000. So that would show you that that must be a +2 charge, because when you got to the third ionization energy, that was the removal of the third electron. That one's so hard, and that's because it must have became a noble gas configuration or in the energy level beneath it. Following that? And you'll have homework questions to do that with. All right, moving on. Electronegativity. This is the last one. Electronegativity and electron affinity, again, are very similar, but electronegativity is the element's ability to attract electrons in a chemical bond. The electrons will spend more time around the more electronegative element in a chemical bond. So this is an example. Hold my bond. We're bonded, except I'm more electronegative. So keep holding, stretch your arm, and come closer to me, and closer, and closer, and closer. And so this is what it's going to look like, right? So that just means that we're sharing electrons. Our hands are electrons. We know in a covalent bond you share electrons, except the electrons are going to spend most of their time around me, which means that I get most of the electron density. Get it? If she's more electronegative, then I'm like this. It's just you're still sharing, but one of them is being an electron hog, basically. Now, if it's electron affinity, it's here's my atom, and I'm trying to acquire an electron from outside. So the smaller I am, the easier it is to grab my electron. The bigger I am, the harder it is to grab my electron. So it's still the same idea. So size, again, is going to play a big role in electronegativity. So the general trend for electronegativity is the top right, but we don't include what? Noble gases, because what do you know about noble gases? They don't want to do anything. They don't want to bond. So they're not going to really be involved in a chemical bond. We'll see later when we get to chemical bonding. Some of the noble gases do in fact bond, but in general, they don't have an electronegativity value. So we're just going to say that the strongest, the most electronegative is fluorine. Why is fluorine the most electronegative? Because it's the smallest atomic radii on this trend of the periodic table. So the smaller atomic radii means that its nucleus is closest to the electrons in that bond, and so the electrons are attracted to that nucleus more than they are in the bigger atom. So again, it's all going to be back to size. So electronegativity increases as atomic radius decreases. When two atoms are involved in a chemical bond, the valence electrons will experience a greater attraction for the positive nucleus that is closest to them. So if I'm standing here and Argo's there and we're bonded, I'm smaller, so I get more attraction to my electrons in that bond than he can. Get it? It's pretty much how it works. So you can almost determine then, too, about bond length based on the atoms and their size, and where the bond will spend most of the time. So you'll see sometimes we draw like HCl. If we're drawing HCl, we know that chlorine is more electronegative, so we'll draw something like this showing that the electronegativity is slightly more negative on this side of the atom, and this side is slightly more positive. Do you remember we drew stuff like this? So when you show electronegativity, you can show it by drawing this S negative and then this S positive. And then you'll see in some slides, we draw density balloons almost to show where most of the electrons are headed towards. Another demonstration is when you draw it like this. When you put this little, I don't know, hash here, it's indicating that this one's positive on this side. And then the arrow points to the more electronegative one. I think that's it, right? All right, any questions?